Hey everyone. So in today's class, we are going to study about principal component analysis, which is basically an unsupervised learning technique. Let's revise again what machine learning is and what are the different varieties of machine learning. So machine learning is we enabling the machines to learn from the data. There are three main categories. One is called the supervised learning, then the unsupervised learning, and then the reinforcement learning. In supervised learning, we work with the labeled data. In unsupervised learning, we work with unlabeled data, that is, we don't have a target to predict. And in the previous class, we discussed clustering, which was one of the unsupervised learnings, where we had to actually group the data into clusters or groups. And we also discussed about association rule mining, which is another unsupervised learning technique. Then moving on to reinforcement learning. In reinforcement learning, we actually have an agent, and that agent interacts with the environment, and it's basically a dynamic programming method in which the agent tries to interact with the environment and maximize its rewards and minimize its punishments. Okay. So principal component analysis is basically an unsupervised learning technique. That means here we are working with what data? We are working with unlabeled data. Now, why do we need principal component analysis? Because of the curse of dimensionality. What is curse of dimensionality? That is when your data set has lot of dimensions or lot of features. For example, you have a data set which has 1 million records, 1 million, maybe let's say 1 billion. 1 billion records are there and we have 10,000 features. So if you see, this data is huge. The number of features are very, very high. So when the number of features are high, it's very difficult to analyze the data, visualize the data, and also to train the model or to build the model. So that's why this is a problem. This is called the curse of dimensionality. Is that fine? So this is the problem that we have, which is called curse of dimensionality. And to deal with curse of dimensionality, what we do is we do dimensionality reduction. What does dimensionality reduction means? Reduce the number of dimensions. Dimensions means features. Reduce the number of dimensions. Now there are multiple ways to do dimensionality reduction. That is, one is feature subset selection and the next is feature extraction. In feature subset selection, what do we do is we have 1,000 features, so we take the top important 100 features only, or top 100, or top 10, or top 20, whatever is the number that you want. You take the top features which are the most important ones. Whereas in feature extraction, what do we do is we convert. We don't take these 1,000 features which are already there, we convert them into new features and then take them. And one of the techniques here is principal component analysis. Okay, now I'll explain you a bit about principal component analysis. So here what we have is, let's say we have 10,000 features, say F1, F2, F3, and so on till F 10,000. So what do we do in principal component analysis is we actually convert these are all our independent attributes, right? So what do we do is we convert these 10,000 features into new 10,000 features, which are called PC1, PC2, and so on till PC 10,000. Now, what's the advantage of having these? The advantage is that this feature is going to contain, the first one is going to contain the maximum amount of information or variability of the data. The second one will have second most important, second most content or variability or information of the data, and followed by PC3, PC4, and so on. So if this contains, let's say, 60% information of the data, this might contain, let's say, 20 or 25% information of the data. The next would contain probably 15% information of the data, and so on. So basically, the first few principal components, they are going to contain the maximum information, and you can take the first 5 or the first 10 and then use only those principal components, use only those new features that you have made, and just ignore the other ones. So in this way, you will be able to grab 90% or more than 90% of the information of the data. Again, it depends on you how many principal components you need, how much information of the data you want to capture. Okay. Now, what do I mean by variability or information? So if let's say we have a feature which is always one, is that feature important for our analysis? No, it is not, because for all the records it's one. So here we have zero variability or zero information. So this feature does not have any variability or it does not have any information. Whereas those features which have high variability, they will have a lot of information, and that's what variability and information we are talking about. So basically, the first principal component will have the maximum information or the variability of the data, followed by principal component 2, followed by principal component 3, and so on. And we take the first few principal components. So that's basically the gist of PCA. Now in PCA, we are actually going to take matrices into consideration. So we are going to basically have matrices and we are going to work with matrices, and we also will be dealing with covariance matrix. So for that, we actually start off with matrices so that we are clear on what matrices are, and then we move into PCA. Okay. So first question to you, what is a matrix? This is something simple and I want everyone to answer this. So, a matrix is basically a rectangular arrangement of numbers into rows and columns. So, basically, if you see something like your data set, you have multiple columns. Each of the column is basically this, and then we have records. So, records are rows. So, basically, a rectangular arrangement of rows and columns is the matrix. Now, there are different types of matrix. I can explain you all of them here. So first of all, what is the size of the matrix? Let's say we have 1, 2, 3, 4, 5, 6. If this is the matrix that you have, if you see there are two rows and the first row, second row, and there are three columns, 1, 2, and 3. So the shape of the matrix or the size of the matrix is going to be rows into columns. You don't have to multiply the rows and the columns. You just have to write R cross C. So basically it will be number of rows is 2 and the number of columns is 3. So you don't have to multiply 2 into 3 and give the answer as 6. No, it will remain as 2 into 3, which tells basically 2 is the number of rows and 3 is the number of columns. Now, let's understand the matrices first so that we can move to PCA. So first of all, what is a column matrix? A column matrix is a matrix which has only one column. For example, like this. So here the size is basically 4 cross 1. That is, there are 4 records and 1 column. So if you have only one column, then that matrix is called a column matrix. Similarly, we will have a row matrix. In row matrix, what we have is, if it's something like this, then there is only one row. That is, what would be the size? It would be 1 cross C. So here the number of rows is 1, whereas in column matrix, the number of columns is 1. Now there's something called as square matrix. So now what is square matrix? A square matrix is basically the one in which the number of rows and the number of columns are equal. So it's 3 cross 3. So number of rows is equals to number of columns. Now, moving on to the next type of matrix, which is called diagonal matrix. So what is diagonal matrix? It is a square matrix in which all the non-diagonal elements are 0 and all the diagonal elements, basically the first primary diagonal elements, are actually non-zero. So here you will have non-zero values and rest everything is going to be 0. So it is a square matrix in which the diagonal elements are non-zero. The primary diagonal elements, that is, only this diagonal elements are non-zero and rest everything is 0. So this is a diagonal matrix. So basically all the square matrices, they are not diagonal matrices, but all the diagonal matrices are square matrices. Moving on to the next matrix, which is called scalar matrix. A scalar matrix is basically the one in which the diagonal elements are actually equal. So it's basically a diagonal matrix in which the primary diagonal elements are equal. So for example, 6, 6, 6. So it is a diagonal matrix, right? In which only the no, in the primary diagonal elements are non-zero. But here, all of these elements, primary diagonal elements, are actually equal. So it is a diagonal matrix, but in which all the primary diagonal elements are equal. Okay. So again, all the diagonal matrices are not scalar matrices, but all scalar matrices are diagonal matrices. So how does it actually work? It's basically, if you draw a Venn diagram, this is basically all the square matrices. Okay. Then inside that you have some diagonal matrix. And inside that you will have some scalar matrix. So all the square matrices are not diagonal matrices, but all the diagonal matrices are square matrices. Similarly, all the diagonal matrices are not scalar matrices, but all the scalar matrices are diagonal matrices. Okay, now the last one, a square matrix in which the diagonals, all the diagonal elements, all the primary diagonal elements are 1 and rest everything is 0. That is called a identity matrix. That is called a identity matrix. So basically it is a scalar matrix only in which all the primary diagonal elements are 1. Okay. So that's pretty much the definition of all the matrices. Let's see a question. If a matrix has 24 elements, what are the possible orders it can have? What are orders? Orders are basically the shape of the matrix. So one order is 1 cross 2, the next order can be 2 cross 1. So basically, if there are 24 elements, how many possible shapes your matrix can have? I'll give you a minute to think about it. Let's see. So if a matrix has 24 elements, then basically it could be, let's say the size could be 1 cross 24. That is, it is basically a row matrix, a row in which we just, it's a row matrix in which we just have one row and all the 24 elements are there are 24 columns. Or it could be 24 cross 1 because the total number of elements has to be 24. So this means that the total number of elements are 24. This also means the total number of elements are 24. Similarly, we can have 2 cross 12. In 2 cross 12 also, we'll basically have two rows. In one row we'll have 12 columns, in another row we'll have 12 columns. So in total it will become 24 elements. Similarly, 12 cross 2. In 12 cross 2, what would happen is we'll have 12 12 rows, but the first column will have 12 elements, the second column will also have 12 elements. So in that way also we'll have 24 elements. Then similarly we can have 3 cross 8 and 8 cross 3. Then similarly we can have 6 cross 4 and 4 cross 6, right? So how many are there actually? 1, 2, 3, 4, 5, 6, 7, 8. So basically 8 possible orders are there. Okay. Now, what if the matrix has 13 elements? What will happen if there are 13 elements? So if there are 13 elements, the possible orders are just 1 cross 13 and 13 cross 1 because 13 is a prime number, so we cannot make 13 with other numbers. So there are only two possible orders. Okay, so now let's move to what is transpose of a matrix. So, transpose, what does transpose of a matrix means? Let's say we have a matrix like this. Okay. Now, a transpose of matrix means that the rows become column and the columns becomes row. So we have the first. So if this is A, I want to figure out what is A transpose, right? So this is the first row that I have. This first row will actually become the first column, that is 1, 2, 3. Then 6, 8, 7 is the second row, so it becomes the second column, 6, 8, 7. Then 4, 3, 2 is the third row, it becomes the third column, like this. Now, if you see the first column, it is the first row. If you see the second column, it is the second row. If you see the third column, it is the third row. Okay, so in transpose, what happens is the rows become column and the columns become row, and it is denoted by A transpose. So if A is the matrix, then the transpose is denoted by A transpose. Now, let's go to the next one, which is matrix addition. So the addition of matrices can only be possible if the number of rows and the columns are the same in both the matrices. So for example, 1, 2, 4, 6 plus 8, 1, 3, 2. You can only add two matrices when the size is the same. Okay, let me explain it with one more example. So here the size is 2 cross 3 and I need one more matrix. Again, the size should be the same. So you can only add them when the size is same, right? So what would this be? Now, when you're adding two matrices, then basically the corresponding elements have to be just added. So basically, the first row, first column elements need to be added. So they'll be 1 plus 1, and the first row, first column element would become 2. Then the first row, second column elements need to be added, which is 3 and 1. So basically, that becomes 3 plus 1, that is 4, becomes the answer of the first row, second column. Similarly, 8 plus 1, it will give us the first row, third column element, which is 9. Then 2 plus 0, it is 2, which is the second row, first column element. Then 6 plus 1, it will become the second row, second column element, which is 7. Then 7 plus 1, it becomes 8. So we get a matrix of the same size, and basically we have to add all the corresponding elements. And same is in the subtraction as well. Now, if you have, let's say, a scalar quantity that is a constant and you have a matrix, and if you want to multiply this scalar with the matrix, then what happens is this 4 is multiplied with all the elements, in the matrix. So it would basically become 4, 4 into 1, 4, then 4 into 2, 8, then 4 into 1, 4, 4 into 4, 16, 4 into 6, 24, 4 into 2, 8. So basically, this constant is multiplied with all the elements. Now, moving on to the matrix multiplication. So in matrix multiplication, what do? We have two matrices. So 1, 2, 6, 3 multiplied by 4, 1, something like this. So first of all, two matrices can only be multiplied. First, let's find the size of it. It's 2 cross 2, and here the size is 2 cross 1. The matrices can only be multiplied when this is the same. That is, the number of columns of the first matrix should be equals to the number of rows of the second matrix. I'll again repeat, we can only and only do the matrix multiplication when the number of columns of the first matrix is equals to the number of rows of the second matrix. Then only we can do the multiplication. And what would be the size of our resultant matrix? Resultant matrix size would be 2 cross 1. Basically, it will be the number of rows of the first matrix into the number of columns of the second matrix. So basically, the size would be 2 cross 1. Then how do we do the multiplication? We do the multiplication as first element would be take the first row and take the first column. That is basically do 1 into 4, which is 4, and then do 2 into 1, which is 2. So the first element becomes 6. So you basically take the first row and the first column and multiply the corresponding elements. Okay. Then for the second element, you take the second row and the only column that you have, that's the first column. So 6 into 4, which is 24, plus 3 into 1, which is 3. So 24 plus 3, which is 27. So this is how you get the matrix multiplication. Okay. So let's probably take one example and then see. So 1, 0, 0, 1. So basically this is the identity matrix and we have 1, 4, 8. Okay. 1, something like this. Okay. So basically the size of the first matrix is 2 cross 2 and the size of the second matrix is 2 cross 3. Since the number of columns of the first matrix and the number of rows of the second matrix are the same, we can do the multiplication and the size of the resultant matrix would be 2 cross 3. That is basically the number of rows of the first matrix into the number of columns of the second matrix. Okay. And let's do the multiplication. So basically for the first element, we'll have basically 2 cross 3 matrix, right? 2 cross 3. So you take the first row and the first column and just multiply the corresponding elements, which is 1 into 1 plus 0 into 4, so it becomes 1. Then for the next element in the first row, what you do is you take the first row and the second column. So 1 into 2 plus 0 into 4, so it becomes 2. Then for the next element in the same row, you have to take the first row and the last column. So 1 into 6 plus 0 into 8, which is basically 6. Then the next row that you have to take the second row and the first column, second row of the first matrix and the first column of the second matrix. So 0 into 1 plus 1 into 4, so it becomes 4. Then you have this second row of the first matrix and the second column of the second matrix. So 0 into 2 plus 1 into 4, so it becomes 4. Then what do? You take the last second row and the last column. So 0 into 6 plus 1 into 8, which is basically 8. Okay. So if you see, this is basically the same matrix and you've got the same matrix back. So essentially this is the identity matrix, and let's say if this is A, then it actually becomes equals to A itself. Or if you want to write it in another way, so basically if you multiply the matrix with the identity matrix, you get the same matrix back. That's what I wanted to show. Now, the next concept is symmetric and skew symmetric matrices. So if you see this matrix, let me show with an example. If you see this matrix and try to figure out its A transpose. So basically the first row becomes the first column. So this becomes 1, 1, minus 1. I write it like this. Then the second column is 1, 2, 0. And the next column is minus 1, 0, 5. So now if you compare the columns and the rows, doesn't it seem similar to A? It's exactly the same as A, right? So A is equals to A transpose. So when you have a matrix of this format where A is equals to A transpose, in that case, that is called a symmetric matrix. What does a symmetric matrix means? So obviously you exclude the primary diagonal elements, but then if you see the first row second column element, it will be equals to the second row first column element. If you see the first row third column element, then the third row first column element will be the same. So this is what happens in the symmetric matrix. Okay. Now Let's talk about skew symmetric matrix. In skew symmetric matrix, what happens is the A transpose is not equals to A, but it's actually equals to minus A. So one example that we have is, let's say our A is 0, 1, minus 2, minus 1, 0, 3, 2, minus 3, and 0. So let's try to figure out what the A transpose would be. So basically 0, 1, minus 2, it becomes the first column. Then 1, minus 1, 0, 3, it becomes the second column. And 2, minus 3, 0 becomes the third column. Okay. So if you see, here, are A equal is A equal to A transpose? No. But if you take a minus sign out of it, so basically if you take a minus sign out of it, it becomes 0, 1, minus 2, minus 1, 0, 3, and then 2, minus 3, 0. Now this is basically your A. So your A transpose is basically equals to minus A. So that type of matrix, that is called the skew symmetric matrix. So A is the skew symmetric matrix. So what happens in skew symmetric matrix is, ignore the primary diagonal elements, but if you see the first row second column, then it will be the negation of the second row first column. If you see the first row third column, then it would be the negation of the third row first column, and so on. Okay. Now moving on to the next concept, which is actually important for us, which is the eigenvectors and the eigenvalues. So let's take an example. We have 0, 5, minus 10, then 0, 22, 16, 0, minus 9, minus 2. So this is our A, and then basically what we are trying to do is we are going to multiply. This is 3 cross 3. We are trying to multiply with a vector, a column vector, which is basically minus 5, minus 4, and 3, which is basically of the size 3 cross 1, since this is same. So you can actually do the matrix multiplication, and what you're going to get is basically the size 3 cross 1. Okay, let's do the multiplication. So 0 into minus 5, which is 0. 5 into minus 4, which is minus 20. Then minus 10 into 3, which is minus 30. So minus 20 and minus 30 will become minus 50. Okay. Moving on the next element. The next element would be 0 into minus 5, which is 0. Then 22 into minus 4, which is 8, minus 88. And then 16 into 3, which is plus 48. So it becomes minus 40. Then we have this. So 0 into minus 5 is 0. Minus 9 into minus 4, which is 36. And minus 2 into 3 is minus 6. So it becomes 30. Okay. Now, can I take out 5 common? Can I basically actually take out 10 common from here? So it becomes minus 5, minus 4, and 3. Now, if you see, this column vector and this column vector are the same. So basically I can write, if this is my A, this is my X, I am getting 10x here. So 10 can be a constant, which I can write it as lambda. Okay, that's what I can write as lambda. So basically AX is equals to lambda X. So here X is called the eigenvector and lambda is called the eigenvalue. So basically X is the eigenvector of A and lambda is the eigenvalue corresponding to the eigenvector X. So basically when we have a matrix A and we try to multiply it with a vector and we get the vector back again, only change, the direction does not change, but only changes in the magnitude, then that vector is basically called the eigenvector of that matrix, and the corresponding value lambda is the eigenvalue. Okay, so that's the concept of eigenvectors and eigenvalues. So eigenvector of a matrix A is a vector which is represented by a matrix X such that when X is multiplied with the matrix X, then the direction of the resultant matrix remains the same as vector X. Now, one more concept. If you have A and you multiply it with B and you get the identity matrix, then this B is actually called the inverse of A matrix. That is, you can write it as A inverse. Okay, so basically A into A inverse is the identity matrix. Okay, so A inverse is basically a matrix which is when multiplied by A, you get the identity matrix. Now, these were all the concepts of matrices that we discussed. Now, why did we discuss all these concepts? We discussed them because we all want to understand principal component analysis. Okay, so now let's start off with principal component analysis. So, principal component analysis or PCA is basically a dimensionality reduction method. Basically, we are trying to reduce the number of dimensions because the number of dimensions of features are very high. And when the number of features or dimensions are very high, we are suffering from the problem which is called curse of dimensionality. And basically, what's the problem when the number of features are high? It's very difficult to actually build the model, analyze the data, visualize the data, and so on. So those are the problems that we face. Okay. So what do we do is we convert the 1,000 features that we have into some new 1,000 features. That is what we do in PCA, right? We convert it into new 1,000 features and then take the first few principal components only. So obviously, reducing the number of variables of a data set naturally comes at the expense of accuracy. Obviously, if you take the first few principal components, you might be having 95% of the information of 95% information of the data or 96%, but you're still losing on some information, right? So obviously, it's coming at the expense of accuracy. But the trick in dimensionality reduction is that you trade a little accuracy with some simplicity. Obviously, you are taking 95% or 96% of the information or even 90% of the information, but it is making your model or it is making your data much more simpler. So you're trading a bit of your accuracy with simplicity. Because smaller data sets are easier to explore, visualize, and it obviously is easier to build the models on that. So idea of the PCA is simple: reduce the number of variables of a data set while preserving as much information as possible. Try to take the maximum information that's possible. But we are obviously taking the first few principal components so that we have the maximum variability or the information of the data, but we just don't have it 100%. We might take the first few principal components and be able to grab some 90% or 95% or 96% information of the data. So how do we do this? We have 5 steps, and we'll understand all of them. And we start off with the first step. So what do we do is, let's say we have a very big data which has, let's say, 1 billion records and there are 10,000 features. So this is the data that we have. The first step is to do the standardization, that is convert the data into standardized format, that is do the feature scaling. So basically, what is standardization? You have your X column. So what do? You transform it into X minus mu by sigma, where mu is the mean of the column and sigma is the standard deviation of the column. So now this transformed feature will basically have the mean as 0 and sigma as 1. So this is basically the first step in standardization. Now, why are we doing this? Because in the second step, we will be creating the covariance matrix, and covariance matrix is affected by the original values. And basically, the reason here is that obviously standardization is critical in PCA, and the reason is that PCA is quite sensitive regarding the variance of the initial variables. That is, if there are large differences between the range of initial variables, those variables with the larger ranges will dominate those with the smaller ranges. And also in the next step, we will have the covariance matrix that will be built, and covariance matrix is affected by the initial values. So we don't want our covariances to be affected by the initial values. If they are bigger, like if a column has bigger values, so for example, let's say there are three columns, X, Y, and Z. Okay, so if in X and Y you have bigger values and in Z you have smaller values, then covariance of X and Y is going to be higher just because X and Y had bigger values, not because the relationship between them is stronger. Okay, so that's why we are going to standardize and then only move to the next step, because we don't want some features to dominate over others. That's what we do in the first step, which is standardization. Okay. In the second step, what do? We basically create the covariance matrix. Now, let's say we have three features. Obviously, here we are only talking about the independent attributes. We don't have any target or any dependent attribute. Now, the second step, what we will do is basically create the covariance matrix. Now, what is covariance? It basically tells us the direction of the linear relationship between the two features. So, if there are three features, then we'll have a 3 cross 3 covariance matrix. If there are four features, we'll have 4 cross 4 covariance matrix. If there are n features, we will have n cross n covariance matrix. So, how does the covariance matrix look like? So basically here you write XYZ, here also you write XYZ. And here in the first element, you find out the covariance of X and X. In the second one, you find the covariance of X and Y. In the third one, you find the covariance of X and Z. In the in this element, you find the covariance of Y and X. Then here you find the covariance of Y and Y. Then you find the covariance of Y and Z here. Then here covariance of Z and X. Then covariance of Z and Y. And then covariance of Z and Z. Okay. So basically, this is the matrix that we get. Okay. Now, if you see, what is covariance of X and X? It's actually the variance of X only. You're not comparing X with something else. You're just comparing it with X. So it's basically variance. Similarly, this would be variance of Y and this would be variance of Z. Okay. Now, if you see, now one more thing that you know is covariance of x comma y is equals to the covariance of y comma x. So the relationship that x has with y, the same linear relationship y will have with x. And here we are only talking about the linear relationships. So essentially, both can be written the same, or what we could do is, instead of one, like instead of writing like this, we could write it as covariance of y and x. Okay. Then again, covariance of x and z can be written as covariance of z and x. Then again, covariance of y and z can be written as covariance of z and y. Now, if you see, can we say that this matrix is symmetric? Yes, it is, because here all the primary diagonal elements are there fine. But if you see, the corresponding elements are the same. So the first row, second column element and the second row, first column element are the same. Similarly for others. So yes, this is a symmetric matrix. Okay. So we create a covariance matrix in the second step, which is basically the symmetric matrix. Okay. Now, what is the third step? So this covariance matrix is the matrix that we have. In the third step, you find out the eigenvectors and the eigenvalues of this covariance matrix. Okay, so if we have the covariance matrix, which let's say is 3 cross 3, because we had three features. So I can say ABC and DD both are same. Here also EE and FF. So if this is the covariance matrix, then for this matrix, you find out the eigenvectors and the eigenvalues, such that eigenvector would be when covariance matrix is multiplied with that vector, you get the same vector back only the magnitude changes. Now, if you have a matrix which is 3 cross 3, then how many eigenvectors will be there? There will be 3 eigenvectors. So if you have the square matrix of n cross n, the number of eigenvectors that you're going to have are n. Okay. So basically you find the eigenvectors and the eigenvalues. And these eigenvectors are basically the new directions in which are are these are basically the directions in which we are going to have the maximum variability or the information of the data. Basically, these are the directions of the principal components. Okay. So the organizing information in principal components this way will allow you to reduce the dimensionality without losing much information. So let's say we have 3 eigenvectors that we come up with, because this is a 3 cross 3 matrix, right? So the first vector that we have is, let's say, 1, 2, 3. The second vector that we have is, let's say, 1, minus 1, 0. And the third vector that we have is 2, 3, and 5. Okay. The lambda values associated here are, let's say, 2. The lambda 2 associated is 1, and the lambda 3 associated is basically 4. Okay. Now, basically, how much information will be contained? So this is basically the direction of the principal component, one of the principal components. So how much information will be contained in this direction? It will be given by the lambda value of this eigenvector divided by the total lambda, which is 2 plus 1 plus 4. So what is that? It is 2 by 7, right? Similarly, how much information will be stored or in this direction, in this V2 direction, it would be 1 by 7. And for this, it will be 4 by 7. So the maximum information is stored in this. So this is your principal component 1 direction, this is your principal component 2 direction, and this is your principal component 3 direction. So basically, these eigenvectors and eigenvalues are behind the magic, because the eigenvectors of the covariance matrix are actually the directions of the axis where there is most variance or most information. And that's why we call them as principal components. So, and eigenvalues are simply the coefficients attached to the eigenvectors, which give the amount of variance carried in each principal component. So basically, these are the directions in which we are going to be storing our information, and this is basically, if you see, the lambda value is the maximum and it contains 4 by 7% of the information. So this is the direction in which maximum information will be stored, or this is the direction of the first principal component, that is PC1. Okay, followed by the second one, followed by the third one. Okay, so let's say we have 10 features like this. We have 10 features, and basically we know that the first principal component stores 40% information of the data. The second principal component stores lesser than that, obviously, which is around 18%. And third principal component stores around 15%, or not 15, maybe 12%. The fourth one stores around, let's say, 8%. So, and the next one stores around maybe 7%. So let's say if you need 70% information of the data, if you are trying to build a model with 70% information and the variability of the data, then how many principal components do you need? You obviously need the first one because it carries 40% information. The second one carries 18% information, so which is total 58%, and this carries around 12% information, so it's approximately 70%. So basically, if you just take the first 3 principal components and disregard the others, then your 3 principal components, that is only 3 new features, are going to have 70% of the information, and you can disregard the others. Obviously, obviously, since you have 70% of the information, you're using information, but then you are reducing the number of features, that is making your model, making your data analysis, making your visualizations, everything simple. And if you see, The first principal component will have maximum amount of information. Then the second one will have lesser than that. Third will have lesser than that, and slowly it's going to decrease. And the last one will have very less information. So the last few can actually be disregarded. Okay. So this happens no matter whether there are 10 principal components or 100 principal components. So basically the first few principal components will only be taken because they carry majority of information of the data. Okay. An important thing to realize here is the principal components are less interpretable. Now, what we have done is we had initially the features as in our data set, they were gender, SSCP, SSCB, and so on. Now you have converted them into PC1, PC2, and so on. Now, if you see, you don't know what PC1 exactly means. Obviously, you know what gender means, but you don't know PC1, PC2, PC3. They are all of them are actually linear combination of your initial variables, but they are less interpretable. We don't know what they exactly mean. So they are less interpretable. They don't have real meaning since they are constructed from the initial variables. But yes, they are the linear combination of our initial variables, but they are not interpretable. So principal components represent the components of the data that explain the maximum amount of variance. That is, the first principal component will capture majority of the information, followed by second principal component, which has second most information of the data. The third principal component will have third most information of the data, and so on. So by ranking your eigenvectors in order of their eigenvalues, highest to lowest, you will get the principal components in order of significance. So basically, by the lambda value, you can figure out how much information they are storing. Okay, that's the third step. Now, what is the fourth step? The fourth step is feature matrix. So first, what you've done is you have basically converted your initial variables, that is, these were the initial variables. Now you have converted them into PC1, PC2, PC3. So basically, these are the directions in which you will have information stored. Okay. So in feature matrix, what do we do? In feature matrix, we figure out how many variables we want to keep. So basically, since you want to reduce the number of dimensions, here you have three. Let's say now I don't want to keep the three. If I had to keep all the features, then why was I doing this PCA? I was doing this PCA because I wanted to reduce the number of features. So let's say from three features, I wanted to reduce to two features. That is, I'm going to take the first two principal components only. So in feature matrix, what do I do is in feature matrix, I just put these two principal components, PC1 and PC2. You put the first principal component here and the second principal component here. So if you see here, we had this as the first principal component and this has as the second principal component. So in feature matrix, since I want only two features, so I'll first put the first principal component 2, 3, 5 and the second principal component 1, 2, 3. So this is my feature matrix in which I'm taking only the first two principal components. Okay, so this is the second step. Now, basically, these are the directions. This is the first direction and this is the second direction in which we have to reorient our data. So the fourth step was to create the feature matrix. What would be the last step? The last step would be to basically recast the data along these principal components. Obviously, your data looks like what? You have gender, SSCP, SSCB, and so on, right? And here you have some values. Now you know that I want to take these two principal components. Let me write what was there. 235 123. Okay, so basically the feature matrix was 235 123, like this. Okay, so let's say gender, SSCP, SSCB, all were these were only the three features, and we had, let's say, how many thousand records, and these were the three features that were available to us: gender, SSCP, SSCB. Okay. Now, obviously, there were some data here. So gender was, for the first one, it was 1, SSCP was 64. Obviously, we have standardized it. So the values look like 1.2, 1.4, 1.6, and so on. Then 1.5, 2.1, 3.1, and so on. So these are standardized values that you have. Okay. Now, if you see, now, here we have three features. So basically the size that you have is 10,000 cross 3. That is, the number of records is 10,000 and the features that you have are 3. So if you multiply this original data with the feature matrix is 235 and 123. So basically it's 3 cross 2. The number of rows are 3 and the columns are 2. So now if you do this, obviously you can do the multiplication, and finally what you will get is 1000 into 2. So now you will have two columns. The number of records remain the same, which is 10,000, but now the columns that you have are 2. So in this way, you have reduced the number of columns. That is, from 3, you've reduced it to 2. So similarly, if you have many columns, here I use these simple numbers, very small columns to explain you everything. But in general, when you're doing PCA, you will have lots and lots of features, say 1,000 features, and then you are just taking 10 out of them. Okay. So here you will have 1,000 features, and then you will just take 10 first principal components. Okay. So now what you have done is you have reoriented your data. So you're multiplying 1.2 into 2 plus 1.4 into 3 plus 1.6 into 5. That will become the first value. So that is what is recasting your data along these principal components. And that's the last step. So now we have the data that is the number of records are the same, but we have reduced the number of features. Okay, some important points to note about PCA. PCA is basically unsupervised learning algorithm. Okay. The second thing, PCA works well with linear correlated data. Obviously, because you see we have covariance, and which tells us the linear relationship. But PCA does not work well with non-linearly correlated data. And PCA is going to find the principal components which are orthogonal to each other. That is, the directions which you see. They're, so basically, you figured out the directions in which you have maximum variance, right? You had PC1, PC2, PC3, and so on. So all of them, those directions are going to be orthogonal or perpendicular to each other. So if you see this vector and this vector, they are going to be orthogonal to each other. Obviously, maybe here they are not, but in reality, since I just took the dummy values, they are actually, in reality, they are going to be orthogonal to each other. Then, the variance that is explained by one principal component can be figured out by taking its lambda value divided by the total lambda value. Okay, that's basically the important points for PCA. Now, let's see some questions. The first one, let's since we've understood everything about PCA, let's try to answer some questions. Excuse me. So is it important to standardize before applying PCA? Yes, it is very, very important because PCA finds new directions based on the covariance matrix, right? And since the covariance matrix is sensitive to standardization of variables, we need to do standardization. Okay? Because if we are saying covariance of x comma y is some big value, it may be because x and y values are big. X and y feature values are big. It's not that the relationship is stronger. It may happen that it's not about the relationship, it's because of the x and the y values. So covariance is sensitive to basically standardization. That's why we have to do standardization. Okay, so usually we do standardization to assign equal weights to all the variables. If we use features of different scales, we might get misleading directions, misleading principal components. So yes, it is recommended. It is recommended that you standardize before applying PCA. Okay, that's pretty much the answer. Moving on to the next question. Should one remove highly correlated variables before doing PCA? So basically, all the highly correlated variables, for example, sales tax and price, should they be removed? If you have two features, one is temperature in Celsius, other is temperature in Fahrenheit. These all are highly correlated variables. So sales tax and price are highly correlated. Temperature in Celsius and temperature in Fahrenheit both are again highly correlated. So is it necessary to remove these highly correlated variables? No, it is not at all necessary. So PCA is going to load all the highly correlated variables on the same principal component. So all the highly correlated variables are going to go in the same principal component. And what are principal components? They are basically the linear combination of our initial variables only. Okay, the next question. How can you evaluate the performance of a dimensionality reduction algorithm on your dataset? So how do you figure out or how do you evaluate the dimensionality reduction algorithm? Obviously, we discussed evaluation metrics for all, but we did not discuss the evaluation metrics for this. So how can you evaluate this if your PCA worked well or not? So there is no clear way to evaluate your PCA, but a dimensionality reduction algorithm performs well if it eliminates a lot of dimensions from the data set without losing too much information. If it's able to capture, say, majority of the information of the data, and it is obviously reducing a lot of dimensions for you as well, but also ensuring that the majority of the information of the data set is available with you. So in that case, your PCA is good model. So how can you do that? You can first, basically, let me show. So how can you evaluate the model? So what you can do is first build the model. Let's say the model that we are trying to build is, say, linear regression model. And here we have 10,000 independent attributes and one target attribute. Okay. So you build the linear regression model and see your results, RMSE, MSC, and R square, and so on. Now, what you do is in the second in the second wave, what you do is you have these 10,000 features. First, you do PCA for them, and then what you do is you get, let's say, you take the first 10 principal components, and then you put your target also back. Let me write it like this. You put your target also back. So first what you took the 10,000 features, you took the data of all these 10,000 features along with all the records, you converted them into the first 10 principal components, you took that data and then you appended your target, and then you applied linear regression and found your R square and or any evaluation metrics. There should not be much difference between them. You are reducing the number of dimensions, so there would be some loss of performance, but the performance loss should not be very high. That is, your this R square mostly would be lesser than this R square, but it should not be very, very low. Okay, so if the algorithm is performing just as well as the original data set, or if it is performing even slightly lesser than the original one, then it's fine. So basically, this PCA should not reduce your evaluation metrics very significantly. It can obviously be a bit less or almost similar to your this R square, but it should not be very, very less. Okay, and PCA is generally used as one of the pre-processing techniques, and it is used before you actually build your model. For example, here we were building linear regression, right? So it is generally used as a pre-processing step to reduce the number of dimensions, and after that, you build the model that you want to build. Okay. So what? Yeah, this is the answer for it. So if the if you see, if dimensionality reduction did not lose too much of information, then the algorithm should perform just as well as your original data set. So if you are doing linear regression, you try to figure out the linear regression results, that is R square, with the 10,000 features, and then you try to figure out the R square with the 10 principal components. And the R square that you get with the 10 principal components should not be very, very low as compared to the one that you got with 1,000 features. Okay, so this R square should be almost the same as this R square, or maybe a bit, this R square can be a bit less, because obviously you're trading a bit of your performance with simplicity, right? Now, the last question, what are the drawbacks of PCA? So the drawbacks, the first one is that the transform features are hard to interpret. You don't know what PC1, PC2 mean. They are they are linear combination of the initial variables, but they are hard to interpret. And obviously, some information is lost. Here we are trading a bit of simplicity and accuracy, right? So some information is lost, possibly degrading the performance of the subsequent algorithms that you are trying to build. For example, in our case, it was linear regression. And the last drawback could be that it's computationally intensive. It takes a lot of time, a lot of space, because we are dealing with matrices. One last thing that I would like to say is that PCA is generally used as a pre-processing step, and it is used before you build your actual model. For example, let's say you're trying to build your logistic regression model, but there are thousand, or you can say 1 lakh features. Okay. Now, obviously, this is very difficult to build because there are so many features and the number of records are also very, very high. Let's say 1 trillion. So what you will do is first you will do PCA out of after PCA, you're going to take the first 10 principal components only. And with these 10 principal components along with your target, you are going to perform your logistic regression, and you're going to build the model. So you don't take these 1 lakh features, you just take the 10, the 100 principal components or any number of principal components that you want to take. Okay, so PCA is a pre-processing step generally, and it is used before you actually build your model. It's used to reduce the dimensions, and once the dimensions are reduced, then you build the model that you want. Okay, that's all about PCA. I hope that was clear. I have added a few references also. So thank you everyone, and we are going to meet in the next class with the coding on clustering and PCA.